Greetings everyone and welcome to section 8.5. This is where we're going to take the lessons that we've learned in sections 8.1, 8.2, and 8.3 and apply it to a real world problem. So the problem that will govern this section is the spring mass system. Okay, so for our purposes, you have a mass connected to a spring connected to a fixed point, and y equals 0 is the mass extended from the natural length of the spring. When y is positive, it's above the natural length. When y is negative, it's below. dy dt is upward motion. dy dt negative is downward motion. Now, generally speaking, the differential equation that models the position of the mass at any given time is given to you by the y double prime plus b times y prime plus cy equals f of t, where both b and c are positive. C has to be greater than 0. It can't even be equal to 0. The b portion of this is the drag component. Okay, so it's forces that act on the system that dampen the amplitude of the spring and mass. So you're thinking friction, air resistance, stuff like that. F, the non-homogeneous portion of the differential equation, is a force that's keeping the spring mass system in motion. Okay, so it's your hand hitting the mass to keep it oscillating up and down. Okay, looking at our possible outcomes that depend on B and C. One is you have no forcing, so F is 0. Okay, so we have a homogeneous system. Okay, if there's no damping, kind of in an ideal world where there's no friction, air resistance, anything like that, you have what's called simple harmonic motion. So that's when this term is going to be absent. Okay, otherwise, you have weak or strong dampening depending on the value of B. If it's not weak and it's not strong, then we call it critical damping. Okay. With the trig function, okay, you can have no damping. That's where you have multiple frequencies or resonance, or with damping. Okay, and with damping, we're going to look at the equation y equals yt plus ys. Okay, let's see what that means. First off, most simple example of harmonic motion, we have y double prime plus 9y is equal to 0. Okay, solve for y. So we're going to look at the function that solves this differential equation. Okay, so our auxiliary polynomial here is r squared plus 9 equals 0. So r is plus or minus 3i. So the solution to this is going to look like constant 1 cosine 3x plus constant 2 sine 3x. Okay, pretty straightforward. Now, you're told that there are two initial conditions. Y of 0 is 5 and y prime of 0 is 6. So if y of 0, well, before I get to that, y prime is what? It's going to be minus 3 c1 sine 3x plus 3 c2 cosine 3x. Now, if y of 0 is 5, using the first equation, we get 5 equals c1 times the cosine of 0. Cosine of 0 is 1, plus c2 times the sine of 0, that's 0. So that implies that c1 is equal to 5. If y prime of 0 is 6, then we get 6 is equal to minus 3 times c1 times the sine of 0, that's 0, plus 3 times c2 times the cosine of 0, which is 1. So that is going to imply that c2 is equal to 2. And we have the equation y equals 5 times the cosine of 3x plus 2 times the sine of 3x. Okay, so what is that going to look like? Okay, first off, it has a y-intercept of 5, so that's the initial position of the mass. It has a y prime of 0 is 6, so it's got an upward trajectory, and it's going to look something like that, where the peaks and the troughs stay consistent. There's no forcing, so there's nothing that's causing the mass to go above or below the peak and trough, and there's no damping, so that's nothing to cause this thing to kind of fizzle out. What's the distance between the peak and the trough? Okay, well, that's the amplitude. Okay, so for simple harmonic motion, that's of this form, C1 cosine omega t plus C2 sine omega t. It's called simple harmonic motion. The amplitude is given by the square root of C1 squared plus C2 squared, and the period is t, which is 2 pi over omega.